Thousands of AI applications are launching every single day. The market is flooded with new startups, all rushing to integrate large language models into their software, multiplying at a rate we can barely track. But behind the landing pages, the technical reality is often much simpler. Many of these tools function as brittle wrappers, passing user inputs directly to a core language model with very little intervention. This is a Phase 1 application. It is built to take one specific input and return one specific output. A request goes in, the model processes it, and a response comes out. This architecture is entirely stateless. The model functions like an isolated neuron, possessing no memory of its past interactions and no way to reference the history of the conversation. While this creates a convincing demonstration, a stateless prompt is difficult to scale into a defensible software product. In a business environment, software is expected to maintain complex, multi-day operations. A professional user needs a system that can track progress across different sessions. Consider a request like this: find cheap flights to Tokyo, check if my points cover them, and book the best option. A single-pass architecture simply cannot complete this. It has no mechanism to take independent digital actions, like logging into a rewards portal or executing a booking through an API. Raw intelligence quickly becomes a severe bottleneck when it lacks an underlying execution layer to handle the actual work. To solve for multi-step workflows, developers often try to link several single-pass nodes together in a sequence. This is prompt chaining. The first action's output, like finding flight data, pipes directly into the second, comparing it against a budget. But if an API times out, the chain breaks. The second node shatters, the line snaps, and the sequence goes dark. Linear systems lack a feedback mechanism. If the data is messy or a tool fails, the system has no way to evaluate the error or attempt a different route. A linear architecture scales fragility. The more steps you add, the more likely the system is to suffer a catastrophic failure. This fragility demonstrates that linear design is often the root cause of product failure in production environments. While prompt engineering focuses on crafting clever text to guide the model, resilient systems require a focus on the broader engineering environment. This is context engineering. It involves designing the entire structural blueprint that surrounds the AI, moving the focus from the input string to the information architecture. This architecture includes persistent state management, automated retry logic, and direct integration with external data storage. By controlling this entire context window, developers can build systems that maintain consistency across complex, multi-step tasks. Replacing the straight line with a closed loop creates a more resilient, self-correcting pipeline. This is the agent loop. It operates through a continuous cycle: perceive, reason, plan, act, and observe. The addition of the observe step is what changes the dynamic. It allows the system to look at the outcome of its action and determine if the goal was met. If an action hits a blockage, the failure is routed back to the reasoning engine to generate a new plan. Because the loop is persistent, the system securely queries databases and executes code independently, using the results to inform the next turn of the cycle. The loop transforms the AI from a passive text generator into an active software engine. There is currently a significant gap between the capabilities shown in AI demos and what these systems can actually handle in production. Most current AI applications remain restricted by the limitations of Phase 1 or Phase 2 architectures, making them vulnerable to real-world data noise. Future market leaders are building on orchestrated execution layers and autonomous pipelines that are specifically designed to handle those errors. For developers, the goal is to stop shipping stateless toys and begin engineering systems designed to survive inevitable technical failures. In this environment, the durability of the pipeline you build around a model is what determines the long-term reliability of the product.